Oh, there we go. But I'm not working. Or wait, no, this is not working. Oh, good. Test the sound, and we'll test it again. What? Okay. Okay, testing. Wow. Okay. All right. Want to test it again? It's still rather loud in here. I sound good on Zoom. Okay.
On the lights, you got, how do you like the lights?
I don't care.
But I want you to
Doesn't
see your
matter.
face.
It's, I think, I don't know, whichever, I guess you can dim them a little bit. It doesn't matter. Yeah, that should be good. Sure. I'd go for it. What? I have a guy in Nigeria who does that. Yeah, I think he's a prince or something. All you need is to give us the information on your checking account, you know. That's right. Well, it's really not magic. What it is not understanding how things work. So therefore, they're magic. Right. It was like the time I tried to fix a pocket watch. And when I put it back together, I had parts left over. I knew there was something wrong. I I don't comment on that, but I can only get into trouble. No, I don't. But if you, I mean, whatever you want to know, I can send you the reference. It's all, it's all there on Wikipedia and places like that. And all the technology I'm going to tell you about is really pretty old stuff. Nobody understands it, but it's old stuff. Well, it all started when I asked one of my granddaughters, how does a light work? And she couldn't answer. And then I discovered she didn't know how anything else worked in the house. So I figured, well, maybe we would understand some of this technology. We'll appreciate it better. Right. They developed it for use in the airplanes to heat up the food. And I remember it was the radar range, the original microwaves. A trade name. But you have a tube there that generates the microwaves, and the way it works is the water in your food absorbs the radiation and it gets hot. So you can't put metal in the microwave or you'll see a wonderful display. But anything that's non-metallic, and if it contains water, it will get hot. That's why if you put an egg, a raw egg in, you got to punch a hole in it or it's going to explode.
Yes, thank you.
What? Okay.
You got ready to start, Joe?
I'm ready to start.
I got right at 10 o'clock. Good morning,
Is it 10
everybody.
o'clock?
Welcome. I'm starting off the winter term here. And Dr. Burdock here, Berkow, is going to be our first speaker. So Joe Berkow is a retired assistant professor from Johns Hopkins School of Medicine, and he is going to start us off. There you go. And
Okay,
please remember
well,
to silence your cell phones. I'm sorry. Silence your cell phones. Thanks.
okay, well, Happy New Year, everyone. Welcome to the first of the ILR sessions of the new year. And this talk is about the everyday magic in our lives. We live better, more comfortable, fuller lives than kings did 200 years ago. And modern technology, modern science, and medicine made it possible. So the purpose of this series of talks is to explain how all this technology works to make our lives better and more comfortable. So today we're going to talk about magic inside the house. Next week, we'll talk about magic outside the house, like roads and street lights. Third talk about all the electronics that we use, and we use a lot of them. Then we'll talk about transportation, including some of the newer things like maglevs and hyperloops. Food will be the next to last, and our food is more high-tech than you think it is. It's really quite high-tech. Then the very last will be about medicine and the story of modern medicine. And keep in mind that without modern medicine, about 3/4 of us would not be here today. So inside the house, we have lighting, we have air conditioning, a refrigerator, thermostat, central heating. It makes our lives comfortable. We live in an environment that's temperature controlled, and it doesn't matter whether it's hot outside, we can cool it inside. If it's cold outside, we can heat it inside. And we do it fairly efficiently. And then we're going to talk about our modern stove and oven, and then things that we just take for granted, like running water. You turn the tap, and not only do you get water, but it's pure water that's drinkable. And we'll talk about how that comes about. And then finally, sewage. It's an important public health thing. It's not something we generally talk about, but it's important, and it really makes our lives safer. So let's start with lighting. 200 years ago, when the sun set, it got dark, you went to sleep because you didn't have any means of lighting except a candle. And candles don't produce a whole lot of light. Besides, they're expensive. So then we developed oil lamps, whale oil and various other oils, and finally the kerosene lamp. Kerosene lamp was interesting because the kerosene that it burned did not produce a terribly bright flame, but it had a mantle, which was paper or cloth impregnated with thorium. And the thorium produced a very bright white light. And so it was a very efficient means of lighting. And then, of course, the big improvement was the incandescent light bulb, where we had a filament that was heated to bright whiteness. It produced more heat than light, but it was efficient in producing light. And then, of course, we came to the fluorescent light and the compact fluorescent. And so who invented the electric light? Well, Thomas Edison is given credit for it. He got a patent for it around 1880, but other people were interested in this. And so there's a fellow named Lindsay who used a copper wire as a filament, Warren de la Rue who used platinum. And platinum worked very well, but of course it's quite expensive, so it's not practical. And then they used things like carbonized paper, and Edison really did not use tungsten. He used carbonized bamboo, but it was realized early on that if you do this in room atmosphere, these things rapidly burn up. They're not very practical. So you have to do this in a vacuum. And Edison had access to a better vacuum pump. And then a fellow named William Coolidge figured out that tungsten was the best stuff to use. Tungsten is a brittle metal which has a very high melting point, around 9,000 degrees Fahrenheit. So it's a good thing to use in an electric light. It also has what the chemists would call a low vapor pressure, so not much of it fuses away when you heat it to incandescence. And so you had a good source of light, you put it in a good vacuum, and if you notice when you looked at a clear light bulb, the filament is coiled. And in about a 60-watt light, there's about 6.5 feet of filament there. It's all coiled up, but it gives you a large surface to radiate light from. Now, the original lights lasted about 1,200 hours. And then when I was younger, they degraded it to about 1,000 hours. And now if you look at an incandescent bulb, it's rated 750 hours. So they're made to burn out. Now, what happens when a light burns out? Well, what's happening is the tungsten metal is flying away from the filament. It's fusing off. And eventually enough of it goes away that the filament wire gets weak and then it breaks. So if you look at a burned out light bulb, it's got this deposit on the inside surface, which is dark, and that's the darkness of the bulb. It's the tungsten that's fused off from the filament. Now, light bulbs can last a long time. There's a centennial bulb in a firehouse in Livermore, California. It's been burning for 122 years. Now, it's got a carbon filament. It was originally a 60-watt bulb, but now it produces about 4 watts of light. But it's still burning. It's in the Guinness Book of Records. So the next thing we developed was the fluorescent light. And this was a considerable improvement. Now, the circuit was worked out around the 1880s, but it wasn't until 1934 that GE developed a practical fluorescent light bulb. And these were the tubes that we're all familiar with. So how does it work? Well, you've got an electrode at each end, and you've got a circuitry which takes the 110 volts that we have from our sockets, ups it to a high enough voltage that you can produce a stream of electrons down the tube. There's a little blob of mercury which gets excited when this happens, and the mercury atoms hit a phosphor coating on the inside of the tube. And it's this coating that glows white light and gives us the bright light. So basically, what we're doing is kicking up electrons and having a substance which can produce bright light once it gets excited. Now, if you look at your neon lights, they're basically the same type of light. It's a tube which has been evacuated. It's got a gas in it. And the light that you get depends on the gas that you put in the tube. So if you put neon in, it's red. If you put argon in, it's a sort of a deep blue. If you put helium in, it's a pink red. If you put in krypton, it's yellow. And if you put in xenon, it's sort of lavender. And you're all familiar with these lights. You know, they're outside, they're every place. But that's how they work. Now, the next thing that was developed, if you look at comparison of the different lights, your candle is nice, but it doesn't last very long and it doesn't give out a whole lot of light. So if you go up to the incandescent light, it's more efficient, it lasts longer, it's brighter. And then you come to the compact fluorescent light. Now, it took quite a few years to figure out how to make this because the fluorescent light doesn't run off of 110 volts. It requires a higher voltage, and it requires a thing called a ballast, which controls how much energy goes into the light. So to make the compact fluorescent, they had to miniaturize all these electronics. So every one of these bulbs has an electronic circuit in the base that allows the light to work. And it has this curlicue configuration to give it a lot of surface area so you get a fair amount of light out. So it's all in technology. And finally, the last bulb to the right is your LED bulb. And that's more efficient. It runs cooler. It gives out a better light. So the LED is the latest improvement in lighting. And if we compare what it does, if you compare the different lights, a 60-watt light bulb puts out about, roughly 800 to 900 lumens of light. And a lumen is just a measure of the illumination. So by comparison, a candle puts out about 12 lumens. So it takes about 20 candles, or 60 candles rather, to equal one 60-watt light bulb. So our 60-watt fluorescent works for 750 hours, and it runs hot. And in comparison, your compact fluorescent only takes 15 watts of power to produce the same amount of light. And it's warm, not hot. And then your LED puts out the same amount of light using 6 to 8 watts of power. And it lasts 25,000 hours. It's about 95% efficient. And it's cool. And there's considerable advantages to the LED. It has a very long lifespan. It's energy efficient. It's durable. There's no glass to break. The light goes on instantly. It's cool. It's versatile design. And it's environmentally friendly. It has no mercury, doesn't produce any ultraviolet or infrared light. So it's the ideal light to use. Now, when I say it has a long lifespan, the LED is probably going to last forever. What wears out in the LED light are the electronics that are required to make it work. So the question is, what is an LED? What is a light-emitting diode, and how does it work? And basically, what you have are two elements. You have, if you're going to conduct electricity, you're used to conductors, things like copper wires, silver wires, aluminum wires. And you have insulators, things like plastic, paper that don't, they're protective. They won't conduct electricity. A semiconductor is something in between. It will conduct electricity if the circumstances are right. Otherwise, it doesn't. So it's an exotic material, usually of gallium or some exotic substance. And there are two types. You have the N type and the P type. The P type is full of electrons, and they're sitting happily there, and they're not going anywhere unless you apply the proper voltage to them. And then adjacent to it in direct contact with this stuff is an N type, which has holes. Now, they're really not holes. What they are, they're places in the material where electrons can go. So it can accept electrons. So what you do is you hook up a source of electricity, like a battery, and you push electrons into the side that already has a lot of electrons. And what that does is kick the electrons there into a higher energy state. And you've got more than you need, so they're going to go next door to the part that doesn't have a lot of electrons. And so you've got these hyped up electrons going into another part of the semiconductor where they promptly are happy, and then you connect it back to the battery so you have a circuit. So as long as the electricity flows, you're going to have this flow of electrons from one side to the other. Well, what happens when the hyped up electrons get to the other side? They promptly go down to their ground state. So they give up the energy they've been given. And in doing so, the energy that they give up is in the form of light. So you produce a beam of light. Well, this is a quantum device. Things jump from place to place. They don't go smoothly. So the beam of light that they give up is one wavelength, and usually it's red. So that's how it works. The problem is we've had LEDs for about 30 years. They're not new, but the early LEDs were very small. They were all red, and they weren't very bright. It took about 30 plus years to figure out how to make them stronger, how to get more light out of them, and how to make them white. Because what use do we have for a red light bulb? So the other thing that occurs is that how does an LED work? Well, it works off of about 5 to 8 volts of DC current. Now you're taking the light bulb you buy from Publix and you're screwing it into a socket with 120 volts. Well, there's circuitry in the base of that bulb to knock that down from 120 volts to about 5 to 8 volts and to convert the alternating current to direct current to make the bulb happy. If you don't have that, you'll blow out that LED in no time. So the question is, how do we get white light from an LED? Well, there are 3 ways you can do it. One, you can do it like a fluorescent light does it. You have the energy that the LED produces to hit a phosphor, which then glows white and gives you white light. And if you look at your LED flashlight, you'll see a little white blob there. That's the phosphor. The LED's behind it, and that's producing the energy to make that phosphor glow and produce your white light. The other way you can do it is to have different LEDs. If you have red, blue, and green, and you put them together, that gives you white light. So you could have 3 different LEDs there to produce a white light. And the third way is to have a mixture of the two, a hybrid. So you have a couple of different LEDs, but they're hitting a phosphor, and the phosphor is glowing white. The other problem was to get the intensity of the light up, because the original LEDs were very, very weak. Well, that took about 30 years, but they finally managed to do it. So they developed what they called super bright LEDs, and now they're quite bright. So before I left my home in Baltimore, I replaced a floodlight, an outdoor floodlight, and my 250 watt bulb was replaced by a 38 watt LED. Now that LED was the size of my thumbnail, but it gave out that much light. They now have LEDs that will take 500 watts of energy, and they light up ball fields. So all of the lighting that you see out there is going to be replaced by LEDs for several reasons. One, they're cheaper than the lights that are out there. They last much longer, and they use much less energy. So this is the future. Well, the next thing we're going to talk about is refrigeration, because we depend on that. And the basic cycle, the basic physics of it are really quite straightforward. If you look at the bottom of that diagram, you have a valve which allows a liquid to convert to a gas. And in doing so, it takes up heat. And so if we go to the left, you have a coil where this liquid is expanding into a gas, and it's cooling as it goes. So if you push air across that, you'll have a stream of cold air, which you can then direct into your house and have your air conditioning or inside your refrigerator to cool off the inside of the refrigerator. Well, then you take that gas and you compress it and you make a hot gas. And then you have another set of coils, the yellow ones, where you have a breeze blowing across them to get rid of the heat. And that allows the gas to condense again into a liquid. And so this is basically how it works. Your refrigerator works that way, and you need to consider your house as just a large refrigerator, because that's basically what it is when you turn on the air conditioning. So this is the system. You compress a gas to a liquid, it gets hot. You let the liquid evaporate to a gas, it gets cold. And in your air conditioner, the liquid going to a gas absorbs the heat, gets cold. Same thing in the refrigerator. And then somebody figured out you can use an air conditioner to heat, because what are you going to do with all that heat that you get? And if you go outside in the summer when your air conditioner is working, if you put your hand on top, it's hot. It's heat coming out. So somebody figured out, well, let's run the air conditioner in reverse. Instead of taking the cold into the house, we'll take the heat into the house. And now we have our heat pump. So if you just look at the right-hand side, you need a bigger unit to cool your house. So you've got this large outdoor unit, which consists of the compressor. And then you've got the inside unit, which takes the heat, the cold air, circulates it either into the house or into your refrigerator. Now, the problem arises, what do you use as your refrigerant? You can't use water. That goes from steam to water to 212 degrees. So the first refrigerant that they used was ammonia. Now, that's not the ammonia you buy in Publix. That's 7% ammonia dissolved in water. This is the ammonia of industry and chemistry. This is anhydrous ammonia, which is an exceedingly nasty compound. If you get that on your skin, it will go right through to the bone, and if you breathe it, it will kill you. It's nasty. It's also flammable. It's one of the only chemicals besides oxygen that supports a flame, that supports combustion. So it means if you have an ammonia fire, you can't put it out. And the original ice rinks, we had one in Baltimore that was an ammonia system. It worked very well as a refrigerant, but it caught fire. And all the firemen could do was to keep the fire from spreading. So if you were to, say, light a match, it will burn as long as there's oxygen. Well, if you have an atmosphere of ammonia, it will burn in that also. So we have a problem. And they realized they had a problem. You don't want to use ammonia. So they developed Freon. And this was developed around 1929. And this was a tremendous improvement because it was safe, it was non-toxic, it was a good refrigerant. And we used it for a long time until we discovered that the chlorine was killing the ozone layer in the atmosphere. And we need that to protect us from the sun's radiation. So in January of 2020, Freon was banned. And they developed another refrigerant without the chlorine, which is safe, it works, and that's what we use today. Now, the problem was you had to change all the apparatus because you had to use different compressors, but that is what we did. Now, if you see pictures of the old ice boxes, many of them show the ice box on the outside of the house. And the reason is they were leaky. And if you leaked ammonia inside of the house, it was unpleasant. So that was the reason the refrigerators were kept outside. Well, we have heating, which is convenient. We talked about the heat pump, which is just your air conditioner in reverse. And of course, we had fireplaces, but it was easier and better to burn oil or natural gas or coal. And then we developed furnaces, which at first burned coal and then oil. And the problem was, how do you get from the furnace to the house? Well, I remember steam heat, steam radiators, hot water radiators. And the problem was it was nice and warm near the radiator, but it didn't circulate very well. So there were cool spots. Forced hot air was a better way to do it. And so what you did was your furnace had a thing attached to it called an air handler. It's just basically a closure where you had a fan and you forced the hot air into a duct. And now if you look at a house, you'll find that some houses have ducts on the floor, some have ducts in the ceiling. The ones on the floor are the ones that were built before air conditioning because it's more efficient to heat if you have a floor duct for heating. But for air conditioning, you want it to go the other way. Well, the other thing is the thermostat. You don't want to get up all the time to either turn on the heat or to turn on the air conditioner. The thermostat is your automatic switch, which figures out what the temperature is in the house and then decides whether I want to turn on the heat or I want to turn on the air conditioning and when I want to turn it on. It's basically a switch which lets us do that. And there are two ways it can do it. The original way is to use two metals that were not the same, dissimilar, because they expanded differently. Now we use a digital thermostat, which is a resistor, which is sensitive to temperature. And so the resistance changes, and that can trigger the circuitry to either tell the air conditioner to turn on or the furnace to turn on. So how does it work? Well, if you take two different metals and you bolt them together, say a strip of brass, a strip of steel, they expand differently as the temperature goes up or down. And so the brass will expand more than the steel, and you'll get an upward bulge, and that will turn the air conditioner on. It's too warm. Conversely, and when it gets cool, it shrinks more than the steel does. And so it hits another switch at the bottom, tells the furnace to turn on. And you can see in the right-hand side, if you make a coil out of it, you can actually get a thermometer that way because it will move the arrow differently depending on what the heat is. And it's important where the thermostat is in the house. You want it in the place where most people will be most of the time. You want it above the floor level, about 5 feet high. You don't want it on an outside wall. You don't want it near a heating or a cooling duct. So you want it where people are going to spend most of their time. And it's very convenient. We take it for granted, and it usually works very well most of the time. Then we talk about our stove and our oven. We originally had wood stoves. Actually, we had fireplaces. Then we went to a wood stove. And then we went to gas, propane. And these were much more efficient, and we could control the temperature better. And then we went to electric ranges and ovens. And the advantage of that was it's easier to control the temperature. The characteristics are different. You turn off the gas, all of a sudden the heat source stops. An electric resistance wire keeps hot. So in your oven, it's very convenient. The sensor in the oven decides you reach the right temperature, but because the electrode is still hot, it keeps the temperature. So it's easier to control. And so an electric oven is probably preferable to a gas oven. The newest modern thing is an induction stove. And that's the latest, and it's much more efficient. And it works because any metal that is electromagnetic, meaning steel or iron, is sensitive to it's sensitive to a current, an alternating current. So what you have underneath the stovetop is a coil which produces an electric current goes through it. It's alternating about 20 or 30 times a second, and it produces an electric field above it. And the pot that you have there picks up this electric energy and converts it to heat because of resistance in the material. That's how it works. There are a couple things you need to know. The pot has to be magnetic material. So no glass, ceramic, aluminum, or stainless steel. You have to have a special set of pots. No copper. If you've got a pacemaker, that's a problem because you're producing an electromagnetic field. So if you've got a pacemaker in your chest, maybe you don't want to be near an induction range. But the cooking is very fast. The stovetop remains cool, and it's exceedingly efficient. Next thing we take for granted, our toothbrush. Well, the original toothbrush is just that, a brush. It's a little brush that you use, put some toothpaste on it, maybe a little water, and you start brushing your teeth. And then they realized there's a better way to do this. If we make the brush rotate a little faster, so we make a brush with a handle with some batteries and a motor, you've got your electric oscillating toothbrush, which all dentists want you to use now because it's much more efficient at cleaning your teeth. Then we have the sonic toothbrush, which works a little differently. The entire head goes back and forth, so it works more like a old-fashioned toothbrush. And then we have the ultrasonic toothbrush, which doesn't use a motor. It uses a crystal to rotate at a very fast speed. And supposedly that produces a better cleaning of your teeth. So what we have in the ultrasonic toothbrush is a battery, a device that creates a very high frequency, which lets what they call a piezoelectric crystal vibrate. And that's what vibrates the bristles in the brush. Well, the claim is that because it's vibrating at such a high rate of speed, that you get a better clean. You get cavitation of the fluid that's in the mouth, and that this cleans off plaque better. Well, maybe it does. Next thing we need to talk about is indoor plumbing, which is a tremendous advance. You have water on demand, and not only is it fresh water, but it's clean water, it's drinkable, it's safe, and so it's very convenient. And then we'll talk about the toilet and the bidet. So I don't know if you can read this, you don't have to, but I'll tell you what it says. Our supply of water in Gainesville is really quite good. In 1891, the city purchased Bulwar Springs to provide water. And in 1949, we were the first city in Florida, and the third in the nation, to fluoridate the water. And that prevents a lot of cavities in our children. So in 1894, they completed construction on the Bulwar Springs pump house. And just an interesting fact, in 1905, the city of Gainesville convinced the University of Florida to move here with the promise of free water. I think the university was originally going to be in Lake Springs, but we have it in Gainesville because we offered them the free water. Well, in 1905, they needed a better water supply, so they tapped into the Floridan aquifer for additional water. And then in 1976, we got the Murphy water treatment plant. So what about Gainesville water? Well, it's good. The question arises, do we have a problem with lead or any other problems? Well, there are no lead pipes in Gainesville. And even if there were, it wouldn't be a problem because our water is a little bit on the alkaline side. The people in Flint have very good water. It's acid, a little bit acid, but that leaches out the lead in the pipes. And so even if we did have lead pipes in Gainesville, it wouldn't be a problem. The water is tested constantly. It's not just like they take it from the ground. The water gets treated and it gets checked periodically. So we know that our water is safe. So the only place we could get lead in our pipes here in Gainesville is from the solder that's used to keep the copper pipes together. And there's very little of that coming out. So our Gainesville water is from the Floridan aquifer to the Burfree treatment. It's moderately hard. So those of us who came from the north where the water is relatively soft, the first thing we noticed was when we take a shower, our soap and our shampoo doesn't suds up as much as we're used to. And that's because the water's got more minerals on it and it's a little bit more alkaline. Well, we use about 23 million gallons of water a day here in Gainesville, or about 8 billion gallons a year. But we've got a large reserve capacity, 15 wells that hold up to 54 million gallons. So we're pretty well off. Our pH is 8.6, a little bit on the alkaline side, and we have a few minerals in it. Well, the Gainesville water is treated. It's not the way it comes out of the ground. It's softened, it has recarbonation, it's filtered, it's fluoridated, and it's disinfected. And it gets checked every couple years. And if you look at the very bottom, you can get a report from the assessment because the environmental protective folks, every couple years, the last time they assessed our water was 2023. And they do it about every 5 years. So our water is good. It has relatively few minerals in it, but it is a little bit on the hard side. Well, we got to get rid of the water that we use. We don't just dump it on the ground, so we have sewage, and we have to get rid of that. So we have 2 wastewater treatment facilities in Gainesville. We have the Main Street Water Reclamation, and then later we developed the Kanapaha Water Reclamation. And what we do is we take this used water, we let microorganisms work on it to clean it up, and by the time we're finished with it, have it settled, we take these settled microorganisms, we take the sludge, and we use it as fertilizer. But the water that's left over is close to drinkable in quality from the Main Street facility, and it actually is drinkable in quality from Kanapaha, which is a state-of-the-art treatment. So here's our Main Street treatment facility. It was originally built around 1930, remodeled in 1950, and it discharges the water to the Sweetwater Branch, Paynes Prairie, and it enters into the Alachua Aquifer. And so the water that goes back into the ground is clean and it gets reused. You can request a tour of the facility if you want. They'll be glad to show you around. And so the wastewater treatment really, well, in 1977, they constructed the Kanapaha. And then in 1984, they expanded it, they upgraded it, and it currently sends water to Hale Plantation, the Alachua County Kanapaha Veterans Park, Chapman's Fund, Nature Trails, the Water Gardens, and Kanapaha Middle School. The water that comes out of this plant is pure enough and it's drinkable. It's state-of-the-art. Whoops, what happened? Oh, there we go. Next thing we're going to talk about is something we take for granted, the toilet. If any of you have had to use an outhouse, you know that this is a tremendous improvement. And what the toilet is, you see a bowl with water in it, and the tank behind it is really a reservoir of water. You have 2 valves in it, one valve at the top, which allows the water to fill, and you have an overflow valve just in case that valve should fail and it doesn't flood the bathroom. So the water will go into the overflow valve. You have a valve at the bottom, which is controlled by the handle that's outside the tank. So when you want to flush, you just pull on the handle, that valve opens up. and water then drains out of the reservoir and into the bowl. Now you notice there's a curved pipe leading the bowl, and that's a siphon. So when you pull up on the handle, the water comes out of the reservoir. It raises the level of the water in the bowl to the level of the top of the siphon, and then water will drain out from the bowl. And that's how it works. And the older design, which we have here, used a float. So those of you who looked into a toilet saw this copper ball or brass ball floating. And this was the way the valve was closed on the inflow part. The more modern ones have a float that's on the stand, but it works. And this was developed early on. Interestingly enough, the float system was developed in England by a fellow named Thomas Crapper. This is real. I can't make this stuff up. So, who invented the toilet? Well, it was invented in 1596. And so it was built for Queen Elizabeth I by her godson, Sir John Harrington. And it was said that she refused to use it because it was too noisy. And if any of you have used the old water closets, that they have some in London, they really are noisy. But a fellow named Thomas Crapper made these toilets. And so when the GIs in World War I came over to England, they used these facilities, and the toilet became known as the Crapper. Well, so be it. The toilet was actually the U-shaped part, the siphon, was developed in 1775 by Alexander Cumming, and he was granted the first patent for a flush toilet. And this serves two purposes. It allows the siphon to work, but it also forms a fluid barrier to the outside. So gases from the sewage system can't come up into the bathroom. It forms a barrier and a trap. So the next thing we'll talk about is the bidet. We don't have many of them here in America, but if you've traveled to Europe, you know that next to each toilet is a bidet. And for those of you who haven't seen one, it sort of looks like an elongated toilet. You straddle it, and it's an upside down shower. So you have a shower in the bottom, which spritzes water upward. And what it was developed in the 17th century in France, and it was used to clean yourself after you finished using the toilet. So you went over to the bidet, you turned it on, and when you're finished cleaning yourself, you had a little towel there, and that's how you did it. Well, called a bidet because bidet in France means pony. And so they figured it was like straddling a pony. So that's how it got its name. And it was used from the 1600s on. So it's an old piece of plumbing. It's interesting that toilet paper didn't come into use in the Western world until about the mid-1800s. But it was developed in China in the 2nd century BC. And in the 14th century AD, toilet paper was in common use in China. So here in the Western world, a fellow named Joseph Gaiety figured out how to make toilet paper, and he called it medicated paper for the water closet. And it was single sheets. And then around 1882, they developed the paper roll that we're used to today. And what it is, it's paper that's designed to dissolve after a couple minutes in water, so you don't clog up the plumbing. And early on, Great Northern advertised their toilet paper as being splinter-free. So we've come a long way from that to Charmin. So what I've tried to give you is a little insight into the things that make our lives comfortable. We have clean, comfortable living quarters. We have an efficient kitchen, an efficient bathroom. We have light on demand. We have electricity for entertainment. And when you think about it, we really live better today than kings did years ago. So if you have any questions, I'll be glad to answer them. Okay. Walter. All right.
Joe, that was really very well done. I would take what you had done, and it would have been a 3 hour course, and everyone would have been asleep. But you covered it all, and I appreciate it. So thank you.
Thank you.
You asked what use is red light on the submarines and ships at sea at night, where the officer of the deck is. They go to red light because it leaves your eye adjusted to see in the dark.
Right.
So we would have, if I was the officer of the deck at night, having dinner in the wardroom, the quartermaster would bring a set of red goggles that I would wear during dinner. And if I went up to the control room so I could look out the periscope, all of the little fluorescent lights were covered with red,
Hmm.
and it was all red light. And if anybody shone a white light, they were really catching hell.
Right. Well, part of the reason is you're dark adapted under the red light. So if you suddenly go to bright light, you're glared out. And if you go from the bright light back to red, it takes a while for your eyes to compensate.
Another question?
Hi. Ted and I had friends that lived in Wisconsin. And when we were in Wisconsin, we played golf out where Kohler is. And it was, I think, called Kohler. And they had housing for their people, and there's a museum there all about how they discovered it. And it was very interesting. And the whole town was, it was like, not communist, but socialist.
Oh, okay.
So when you talk about, okay, so when you talk about the water treatments,
Yes.
are they now testing for the PFAS chemicals?
Yes. Yes. They're looking for all these particles in the water. They're looking for copper, they're looking for lead,
Sure,
and they're looking for
little plastic.
yeah.
Yeah.
So that, yes, and that gets tested for it. So your water is clean. And, if you look at how the water is cleaned, the microorganisms digest all this stuff and then it's settled out. And then they run it through various things. Sometimes they irradiate it so that by the time you're finished, you've got drinkable water. You may not like the idea of drinking that water, but it's perfectly safe.
Okay, another question?
Thank you for your presentation. You were talking about red light. Could you refer to red light with infrared light for healing?
Where what? I'm sorry.
Infrared light.
Right. Well, you can produce any colored light you want with an LED, depending on the stuff that it's in it. But the original ones were just produce red light. You can now get yellow ones, blue ones, green ones. And the LED is just a light emitting diode. We have diodes that emit things, radiation that's not in the visible light range. So you can get infrared, you can get ultraviolet, you can get anything you want now.
Any other questions? No?
Oh, good one.
One more.
Up here.
Joe, this is a question about induction cooking.
Okay.
The first step is to buy the induction cooktop. That seems like a bit of a hit, but you've just begun your journey as you look for the proper types of skillets and pots to effectively be excited by the magnets in the induction cooktop. And many of us go through a series of experiments carrying our magnets with us in our pocket as we do the final test on the product that contains the liquid or whatever it is you're going to be heating. So the question is, many cooking products, skillets and that sort of thing, or pots, are multi-layered composition, different varying composition um, units that can have the desired effect of spreading the heat, making sticking food not stick so easily, and it becomes some of these products will say induction or induction effective or something, but you discover that there's a variability to how effective these are. For instance, if you use a cast iron skillet, it's always going to be effective.
That's right.
It may scratch the top of your glass plate if you treat it roughly, but others seem to have variable uh, excitability of the electrons within the pan or pot. What can you tell us about how to figure out that so that you don't buy a $200 pot that doesn't work very well?
Well, that's easy. Just take a magnet with you. If it's magnetic, it will work. You have to have a magnetic material. Now, a lot of the stuff is clad. So you might have a layer of copper and a layer of stainless steel. But if it's designed for induction, it's got something there that is magnetic, because you have to have a material that will absorb the electromagnetic radiation. And that's how it works. It absorbs the radiation and becomes hot. So it's got to be magnetic. So it means all of the stuff that you have, your Corningware, your copper pots, your glass pots, they're not going to work. The bottom line is it magnetic?
Any other questions? Any questions on Zoom? You can put it in the chat if you have a question. I don't see any in the chat.
Well, then thank you all very much.
Thank you for coming.
Oh. Thank you. Well, Robert, did I fulfill your expectations? Well, thank you.